SeaPower is a program for preliminary calculation of resistance of hull and the calculation of propellers. And there is a third block added in this revision is fuel efficiency calculation of the propulsion system. Program comprises 34 methods for monohulls, 6 methods for catamarans, and 9 methods for propellers. All these methods are published by various authors, and brief information on each of these methods you will find in manual. But in continuation, I will demonstrate how the program works and will comment various features of the program through one example. As an example, we'll use one high-speed boat with two engines of 260 kilowatts each, and of very high speed. So let's start. Resistance monohulls, and now you see we got on this window we must choose type of the hull we are going to do the calculation for, and there are four groups. You can see semi-displacement and planning hulls, hard chain, and round hulls, and they have displacement and sailing hulls. So in this case, this is hard chain hull, and I picked here Savitsky, VTT, hard chain, and BK series. You can you can tick up to 7 methods at once for comparison, and above the 7 it is not possible. Of course, you end up on only one, because at the end you must choose one result and to proceed to calculation of the propellers. Actually, in this program you can run calculation of propellers completely independent of resistance. If you have some other data, you can go straight to that block, that part, and calculate propeller. Okay, in this case we shall calculate first resistance. After resistance we'll calculate propeller, and after propeller I will calculate efficiency of propulsion system. So 3 methods are selected. We'll press confirm selection, and now let's open the data file, resistance data file. This is interceptor. Here it is. Open. Here they are. So for this type of the hull, you have all information here what has to be entered, and system of entering of data you must tick in each box. If you in the box, once you click in the box, you get information on this bottom line in red. You get it in red, and what you are supposed to enter here. In this case, length on water line. Okay. And if you change it, after every change, you must click enter, and then once you click enter, data is checked, because the program is checking that you are entering just numeric figures here. And if everything is okay, this information in the bottom turn to blue, and you get information accepted. So if whatever you want to change, if you start from scratch, you must fill in all these data, and every data, once you fill it, you must click enter, and again click it, enter. Once you are finished with all of them, you must save it. Save complete file. It means just click here, save, and after that you can proceed with calculation. So let's proceed with calculation. Here we are. Now we got, for all 3 methods, we got 3 curves. That means that all 3 methods are suitable for this type of the hull. And now when we move the cursor in the graph, click wherever you want, and for corresponding X, for example 25 knots here, actually it is 25.07, you can read the resistance according to each of these methods. Yeah, and all this speed is recalculated as well in the speed over square root of length, fluid number, and fluid number based on displacement. Here you can read optimum longitudinal center of buoyancy. This is for information only. In our case, and it is not available for all every range of speeds. I don't know where. Let's see. You see here for 17 knots is not working. See here 19 knots. No. Now yes, for 23 knots up. Yeah, you can read it. Out of that is not. This is just for as well for comparison, for information. In our case, LCB is 10%, what is relatively close to this figure, well, for 23 knots. But let's see for high speed, because we have engines of 260 kilowatts each, 520 kilowatts, and as these figures here, these results are actually delivered power to the propeller. So efficiency of the shafting of all the mechanical system is not included here. By default, it is set to 98. So we should reduce. We should calculate it with. It means that we should have slightly less power on the output. We are losing these 2%. So we'll use it. We'll calculate it with 510 or something like that in total. But first of all, let's choose one of the curves. You see, all metals are mentioned here, and all these three active ones are in dark. If we choose, for example, BK series, you see what we can read. You can read limits of this series. Now everything is within limit. Okay. Then you can go back again, BK series. You can read numerical results. See here, and close. We can read graph. Graph is this one, but graph plus original data. In this method, for these points, resistance was calculated, and then the curve was placed between these values. And then you can go ahead and you can see CFCR graph as well. This is for information only, yeah. Back. And then we can see original numeric results. Those results what we have seen on the graph here. This is how the method is working. You see it is going even from 9 knots, 11, 13, 15, but we set, in our case, we set from 15 to 45, something like that, knots, so all these these figures were disregarded. Of course, they were used for calculation of the curve. Close, and as we are going to use this method, this results for later for efficiency calculation, we'll save this method as a model. We must click save as model, and yes. Now let's go back again here to calculate 37, let's say 37 knots, 37 knots, like this. Okay. And now propeller is enabled, because propeller was disabled when you have more curves here. Propeller is disabled, you must choose only one, and you must choose some figures. You must choose one speed and the power to be able to proceed with propeller calculation. And now let's proceed with propeller calculation. Here we are. Now we can at the propulsion is here set to 0.7, yes, as you said, and for high speed propellers and at high revolutions, wake will be practically 0 and thrust deduction 0 as well. But for each of them I must click enter, and here click enter. Okay, and now let's save it, and for revolutions here is set X. X means that optimum revolutions will be calculated. Actually, will be calculation will be carried out for full range of revolutions, minimum possible for this speed and this power to maximum possible. And let's calculate. Sorry, one thing more. Cavitation control. Cavitation control will put it off. Exclude it in this case, and let's see calculation. Maybe you can use Newton radar cavitating to see what will happen with this. You see, with Newton radar cavitating. Now for full range of revolutions, you see first results we have about 2,200, something like that, about 2,200 revolutions, and this going up to nearly close to 4,000 revolutions of the propeller. We have positive results, and there is slight, not very big variation, but optimum is about 3,000. You see, to about 3,000 revolutions. We can go back, data file, and calculate the same by segmental propellers. This method here. This method gives slightly better efficiency and higher speed. Higher speed, and 3,100, 3,400, we have 3,300, so it is fine. It's practically, we are here, we are nearly here, 3,200, 300, okay, like this, 37 knots, fine. So 3,300, this was just to check where we are in terms of efficiency, and it's pretty good. To proceed with calculation, we'll go back, and we shall enter here 3,300 revolutions, enter, and file, save, and calculate again. Yeah, now we get here only two curves. It is pitch diameter ratio, speed, and on X we have expanded area. You see that by expanded area it is in growing pitch. Sorry, by change of expanded area, pitch diameter ratio is coming down, and the speed practically efficiency of all the propellers for full range of expanded area is very slight difference. So we can read again here like this. We choose, for example, this one, expanded area 0.577, 37 knots, and we can exactly for this propeller we can see KT KQ graph. See how it looks like? Okay, we can read it here, and we can proceed engine selection. Actually, now we will first let's just go back for, in our case, 37 knots. For example, this expanded area 0.6, 0.6, 0.6 speed will be 37 knots. In the pitch diameter ratio is 1.019. So speed, pitch diameter ratio, expanded area, and number of blades is 3. Number of blades is 3, and is 3, 2 propellers, of course. And now we have to take this. This is information sufficient for propeller. Once we have this, we can proceed with KT/KQ graph, and now we'll proceed with the fuel consumption and efficiency of the propulsion system. Select the engine. We go here. We'll select the engine. Our engine is this one. Open. Here it is. So I saved it before. There is a button on the first window. When you start, you can enter the data of any engine. It is very simple. You just put the name of the engine, revolutions. You can full range of revolutions, power for each revolution, and specific consumption. That's all. And you can enter up to 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 9 points. It's more than enough for description of the engine. So now we can do here anything. We can see just to see the graph, but now to continue the calculation, we must select resistance data for fuel economy. Resistance data, now will choose the resistance data file, what we saved during the calculation of resistance. When we save it as model correlation, select, and now we have it here, model correlation, MOC, they have all extension, and our file is interceptor, and we say open. Here it is. Just this is for information to see how it look like, and we have just close it. We can just close it, this one, and now we got a graph with information of propeller diameter, pitch diameter ratio, expanded area, blades, and RPM ratio, propeller RPM, and now we can enter here and do graph readings. Engine RPM, propeller RPM, engine brake power, and this is percentage of MCR, propeller absorbed power, and consumption. This is consumption in kilograms per hour. And consumption per engine. This is by number of engines. Of course, it is double because these information are all for one engine only. So you see here, okay, 256 kilowatts, absorb power 45. If you reduce revolutions. If you reduce revolutions, 5.5, you have propeller is 3,000, then you get you have 238 kilowatts of the engine, and absorbed power is 207, and so on. Next, and the next graph is the final one. What is important and interesting for us is reading kilograms per nautical mile. Kilograms per nautical mile, consumption of fuel per nautical mile. You have here graph numerical values, consumption of kilograms per nautical miles, and this is this curve here. And here is a reading if you want to read, or if it the same way by mouse click. And that's all. That would be all. Just exit. We can exit again and exit. Okay. And click about. That's it. Close.